Consider a motorcycle that has some acceleration. We know that a motorcycle is powered by a wheel. Usually it's just the back wheel with some angular velocity. We know that that wheel has a certain radius and it's generating a certain tangential velocity at the road, which is causing the velocity of the vehicle. But what happens when that velocity gets bigger and bigger and bigger? Well, we call it an acceleration. Now, previously we would have done linear kinematics in order to understand the acceleration of a motorcycle, and we would use the center of mass as a motorcycle. But really what's happening is that the engine is applying a force to increase the angular velocity. And so if you have a change in velocity, that's called an acceleration. This is called linear acceleration. Today what we're going to do is we're going to talk about angular acceleration. Angular acceleration is analogous to linear acceleration in that it's the change in angular velocity instead of the change in linear velocity over time. This little fishy thing is called alpha, and the units are radians per second squared. Now, just like angular velocity, angular acceleration needs to be used with radians. Let's look at how angular acceleration and linear acceleration are related. Previously, we knew that the acceleration was a change in velocity over change in time, and that was linear acceleration. Sometimes this will be called translational acceleration, or the acceleration tangent to the circle. Just like with linear velocity, the tangential velocity, or the tangential change in velocity in this case, is called a sub t. Just like with angular velocity, if you look at the wheel and how it turns, if that angular velocity changes, then we call that angular acceleration. And so how are these related? Well, we have our velocity equals the radius times the angular velocity, and so I can substitute this into my tangential acceleration formula, and so I have a sub t change in radius change in angular velocity over change in time. Well, the radius isn't really changing, so I can pull that out. And so the change in angular velocity over the change in time is angular acceleration, and so this becomes a sub t is equal to r. The translational acceleration is equal to the radius times the angular acceleration. If we rearrange this and put this in terms of angular acceleration is the tangential acceleration divided by the radius. Let's look at an example. Let's go back to that motorcycle. A powerful motorcycle can accelerate from 0 to 30 meters per second in 4.2 seconds. What is the angular acceleration of its 0.32 meter radius wheels? So if I look at just the wheel of that motorcycle, I have a radius. The radius was equal to 0.320 meters. It gives me a time increment of 4.20 seconds. Now that is the change in time, only it's starting from 0, and its final time would be 4.20. The velocity, or we should say the change in velocity, goes from 30 meters per second, and it starts at 0 meters per second. And we want to know what is the angular acceleration of the wheel. And so to put these things into perspective, what we're seeing here is we're seeing a change in velocity over time. That is an acceleration, but it's written in linear terms, so that's a sub t. And it's a line tangent to the wheel. The angular acceleration is going to be that curved portion, so the entire wheel is experiencing the same angular acceleration. At the edge here, which is contacting the road, that is the angular, or the tangential acceleration that we're talking about here. If we moved closer into the wheel, that would be different in the linear sense. All right, so let's go ahead and use the formula AT, change in velocity over change in time. And we'll look at what this acceleration is tangentially. So I have 30 minus 0 divided by 4.2. And after I calculate this out, that's a tangential acceleration of 7.14 meters per second squared. Recall from the previous relationship, the angular acceleration was the tangential acceleration divided by the radius, which we just solved for, so that was 7.14 meters per second squared divided by the radius of 0.320 meters. The meters end up canceling. And so when those cancel, I get radians, which is a unitless unitless value, so radians per second squared. So collectively, the angular acceleration is an example of a non-uniform circular motion. So we have uniform circular motion, which was the angular velocity and the angular displacement, and then you have non-uniform circular motion, which is the acceleration or the change in that velocity. So we have an angular acceleration. There's a lot to kind of put together, so we're going to go ahead and summarize in a table everything that's going on. So we have rotational values and we have translational values. Sometimes it's called linear. You can use those interchangeable. Same thing for rotational. This could be angular or rotational or translational or linear. They kind of go interchangeably. And then we are seeing a relationship between the two. So let's look at that. If we looked at uniform circular motion, we measured position in terms of angle. And so in the linear terms, that would be x. So position versus the angle of where an object is as it goes around this circle, talking about position. The relationship between the two is position over radius. Then we talked about angular velocity, and its linear translational analog would be regular velocity or linear velocity, and the relationship between the two are velocity over radius. And then finally, I can draw a little line here because that is the break between uniform circular motion and non-uniform circular motion. We have the alpha. Its analog in the linear is the acceleration. And the relationship is linear acceleration over radius. We also have a kinematic summary of these variables. So the variables go hand in hand. And so if we make another table of the variables, when we looked at our linear motion, we had, and then translational into rotational, we had the angular velocity, the acceleration, the angular acceleration, and the angular displacement. So we have these uniformly accelerated motion equations, often called the kinematic equations. I'm going to go ahead and write down the linear equations. And we're very familiar with these these are probably written down somewhere on a note card or in your notebooks, and we could find any of these variables if I knew these equations, right? Well, because these variables translate, they're analogous to rotational, and there's relationships between the two of them, we can apply that to the kinematics, and we can use our uniformly accelerated motion equations or kinematic equations of rotation. And all we're going to do is we're going to swap out these variables. So let me go ahead and do that for us. Now, one thing that's really important when using these, this needs to be in radians, where you are going to want degrees for any of your trig functions that you're going to use in two-dimensional motion. So linear kinematics is the exact same as rotational kinematics. There's nothing different in how you apply them. The only difference is the variables, and the variables refer to the motion of an entire object in rotation, whereas the linear kinematics usually refers to a specific point in a straight line motion. So there you have it. You've got linear kinematics and rotational kinematics. You're going to want to put this table in your notebooks and mark it, be able to refer back to it often. Okay, hey, thank you.